In the heart of the savanna, silence hides precision. The African rock python, a predator without venom, relies on pure physics to kill. No chase, no roar, no blood spill. Just pressure. Scientists once believed constriction suffocated prey, but new research revealed the truth. It stops the heart in seconds. Each coil is a calculation, each muscle fiber a sensor reading the impala's pulse. How can a reptile with no legs or claws outmatch one of Africa's fastest animals? And how does it swallow something larger than its own head? This is not brutality, it's biomechanics perfected by evolution. The African rock python, Python cebi, is the largest snake in Africa and one of the most powerful constrictors on Earth. Adults often exceed 5 meters, some approaching 6. Its entire body is a system of levers, tendons, and precision muscles, more than 10,000 working together like hydraulic cables. Each movement is silent, calculated, and slow until it isn't. Unlike vipers or cobras, the python doesn't rely on venom. It uses design. Its skull is built with more than 100 joints, allowing each bone to move independently. The lower jaw isn't fused, it stretches open like a hinge of elastic ligaments. When it strikes, both halves of the jaw move separately, locking around the prey's body before the coils begin to close. Its environment demands perfection. The savanna's edge is a landscape of contradictions, open fields cut by rivers and shallow depressions. Here, visibility favors the impala. Speed and alertness are its only defenses. But the python has something faster than legs: patience. It waits under fallen branches in tall grass or near muddy water holes where antelopes come to drink. Its camouflage blends with the soil so completely that even trained eyes miss it. Infrared-sensitive pits along its upper lip detect heat, reading thermal signatures of passing animals even in darkness. To the python, the impala glows like a moving fire through the grass. Every heartbeat, every breath becomes data. Researchers have found that large pythons can sense the vibration of a mammal's heartbeat through the ground, detecting life before sight. The impala, meanwhile, is the definition of biological agility. Its reflexes rank among the fastest in the animal kingdom. With muscles adapted for explosive acceleration and a cardiovascular system tuned for endurance, it can leap 9 meters in a single bound. Its heart, nearly double the expected size for its body mass, pumps blood at a rate that could sustain a marathon. Against most predators, speed saves it. Against the python, speed never starts. This contrast defines one of nature's purest equations: motion versus stillness. The impala survives by detecting movement, the python survives by removing it. While the impala's eyes scan for motion, the python's body becomes motionless code, an algorithm written in muscle and patience. When biologists studied hunting patterns of large constrictors, they discovered a remarkable consistency. The strike zone is always pre-calculated. The snake positions itself near a choke point, a riverbank, a fallen log, a narrow trail, where prey instinctively slows down. Timing replaces pursuit. Energy efficiency becomes a weapon. From a metabolic perspective, every failed hunt could mean weeks of starvation. That's why the python's nervous system evolved for precision, not risk. Each neuron involved in predation is part of a reflex chain connecting thermal input, motion detection, and motor output. The decision to strike happens in milliseconds, long before conscious processing. It doesn't choose, it executes. To humans, this may look like instinct. To science, it's optimization. A predator that can survive on 1 or 2 successful hunts per year has to make each one count. That's why the python's ambush behavior is as advanced as any neural algorithm. It reads its environment, waits for the signal, a pulse, a vibration, a shadow, and transforms stored potential energy into a single explosive strike. Every part of its anatomy contributes to this purpose. The scales on its belly grip the ground like tire treads, transferring force without slipping. The ribs flex individually, allowing the body to move even when half buried. Its tongue, forked and sensitive, collects chemical particles from the air, decoding scent trails invisible to any mammal. Together, these systems make the python one of the most efficient ambush predators ever evolved. In this design, nothing is wasted, not time, not motion, not breath. The savanna is its laboratory, and patience is its weapon. The python's weapon is not venom, claws, or speed, it's control. Evolution has turned its entire body into a tool of physics. When the strike begins, everything happens in fractions of a second. The head shoots forward at nearly 10 meters per second. Jaws lock onto the target with backward curved teeth. each acting like a hook. But the true power comes from what follows, the coils. Constriction isn't random squeezing. It's precision. Scientists used pressure sensors inside artificial prey and found that each coil adjusts force in response to the victim's heartbeat. Every time the impala's chest expands, the python tightens. When the pulse weakens, the pressure stabilizes. It's a biological feedback loop, a living blood pressure monitor turned weapon. For years, textbooks said that constriction kills by suffocation. But that myth was broken. In 2015, researchers studying boas and pythons discovered the real cause: circulatory arrest. The pressure collapses veins and arteries, stopping blood flow to the brain in seconds. The heart can't pump, oxygen stops. Within 10 seconds, consciousness fades. Death by silence. This method is more efficient than venom. Venom requires chemistry. Constriction uses physics, instant, reusable, and energy neutral. It's the ultimate evolutionary efficiency, one technique, infinite reliability. While a lion spends massive calories chasing prey, a python burns almost none. It waits, measures, executes. Under the skin, this calm predator hides an incredibly complex machine. Its muscles are arranged in long, overlapping chains, giving rotational strength around the body axis. When one segment contracts, another stabilizes. The result is even pressure along the entire prey, no gaps, no escape. Each coil acts as a separate muscle group, coordinated by a central neural circuit that distributes effort evenly. The python's nervous system does something remarkable. It can sense the prey's heartbeat through direct pressure feedback. Each pulse tells the snake whether to squeeze harder or hold. This is why constriction is both fast and adaptive, not chaos but calibration. Imagine that same mechanism applied to a human chest. Just 1 or 2 coils could generate more than 90 millimeters of mercury, enough to stop circulation completely. You wouldn't die from lack of air, you'd faint in seconds from loss of blood pressure. That's how the python kills something twice its size without a single wound. Biologists studying African pythons in the field noticed a behavioral constant. After the first successful coil, the snake always pauses. It's not hesitation, it's calculation. The python listens to the body it holds. The prey's last movements are measured, the force adjusted to prevent muscle fatigue in the snake itself. Evolution has turned energy conservation into instinct. Once the impala's heartbeat stops, the python doesn't release immediately. It maintains pressure for several more minutes, ensuring complete circulatory failure. Only then does it begin the next phase, repositioning its body to locate the head, the entry point for ingestion. Every step of this process represents biological intelligence. From the neural decision to strike to the precise modulation of muscle tension, nothing here is emotional. It's pure evolutionary logic. Minimize risk, maximize success, conserve energy. To human eyes, it may look cold. But to nature, it's perfect design, a life form engineered by millions of years of trial and selection. A predator that kills without sound, without chase, without waste. The python doesn't fight for survival, it perfects it. What seems like brutality is actually one of evolution's most efficient algorithms, a mathematical dance of pressure and pulse. The grass trembles. The impala lowers its head to drink, unaware that its predator has been waiting here for days. Beneath the shallow mud, the python lies in ambush, coiled motionless, heart rate slowed to almost nothing. Every breath of the antelope sends micro-vibrations through the ground, feeding the snake's sensors like data to a machine. When the distance closes to less than half a meter, instinct takes command. The strike is pure mechanics. The python's body uncoils explosively, converting stored potential energy into speed. The head extends with surgical precision, guided by heat detection and vibration mapping. The jaws clamp onto the impala's snout, the most strategic point, preventing a distress call and immediate escape. Before the prey even understands what happened, the first coil wraps around its torso. In milliseconds, the snake's body transforms from camouflage to cage. The second and third coils follow, locking around the chest and abdomen. Each contraction is timed with the impala's breathing cycle. When the antelope exhales, the python tightens, never allowing the lungs to expand again. The effect is catastrophic for blood circulation. Within seconds, the heart begins to fail under the combined external pressure and internal collapse. What makes this encounter extraordinary is its precision. The python doesn't move erratically or thrash its prey. It stabilizes. Using its ribs as anchors, it distributes weight evenly, avoiding self-fatigue. Its muscles work in coordinated waves. While one segment squeezes, another holds tension, creating constant pressure with minimal energy use. Researchers comparing this to human biomechanics describe it as a living hydraulic press. For the impala, evolution offers no countermeasure. Its reflexes, which once outpaced lions and leopards, are useless against stillness. Its heart, evolved to power explosive speed, now accelerates itself into shutdown. As adrenaline surges, blood pressure spikes, the very condition the python's coils exploit. The more the prey struggles, the faster it loses consciousness. Observers have measured this phase lasting less than a minute for medium-sized antelopes. During this time, the python's tongue flickers constantly, not aggression, but data gathering. Chemical cues tell it the exact moment life ceases. Only then does it loosen the first coil, sliding slowly to reposition the head toward the prey's muzzle. Now begins a process that challenges imagination: ingestion. The python's skull doesn't open vertically like ours, it expands outward. Elastic ligaments stretch, and paired jawbones walk alternately over the prey, pulling it inward centimeter by centimeter. The glottis, the breathing tube, extends forward like a snorkel, allowing the snake to breathe while swallowing something many times wider than its own head. The act seems impossible until you remember the physics. The skin of the python can stretch up to 150% of its resting diameter without damage, supported by a lattice of collagen fibers. Internal organs shift to accommodate the volume. The heart moves aside, lungs compress, and the digestive tract prepares for chemical warfare. During feeding, the python's metabolism shifts from near zero to hyperactive. Oxygen consumption multiplies, heart rate triples, and digestive enzymes flood the stomach cavity. Scientists comparing energy use found that a single large meal can sustain the snake for months, a biological efficiency unmatched by any mammal. Through every stage, strike, constriction, swallowing, the python demonstrates not chaos, but engineering. Each action is timed, measured, and optimized. The impala's body disappears not out of hunger, but necessity. In a world where survival depends on precision, waste is death. What looks like a brutal act is, in reality, the most refined expression of nature's logic, a predator designed to erase movement, not create suffering. Inside the python, silence becomes chemistry. Once the prey is swallowed, an entire biological factory awakens. The snake, that was nearly motionless moments ago, now becomes one of the most metabolically active animals on the planet. Its heart rate, previously slowed for energy conservation, surges up to 3 times higher. The digestive system turns into a living acid reactor. The stomach releases one of the most corrosive mixtures found in nature, a combination of hydrochloric acid and specialized enzymes that can dissolve bone, muscle, and organs. Measurements from laboratory studies show that the pH inside a feeding python's stomach can drop below 2.0 within hours, comparable to industrial acid. Every structure of the impala, except for its hair and a few keratin-rich hooves, will be broken down and absorbed. This transformation isn't constant, it's conditional. When the python hasn't eaten for weeks, its organs partially shrink to save energy. The liver, intestines, and heart can reduce their mass by more than 40%. But once a large meal enters the body, they rapidly regrow. Within 48 hours, the small intestine doubles in size, blood vessels expand, and enzyme production multiplies. Scientists call this metabolic activation, a phenomenon that inspired research into human organ regeneration and extreme metabolic control. While digestion is underway, the snake's internal temperature can rise by several degrees, a metabolic fever. The increase accelerates enzymatic reactions and speeds up chemical breakdown. Infrared imaging of pythons after feeding shows the entire body glowing with heat from within, like a slow-burning furnace. The python's circulatory system also adapts. Blood flow is redirected from the muscles to the digestive organs. The heart pumps more forcefully, supplying oxygen to tissues that have become biochemically hyperactive. Oxygen consumption spikes by more than 40 times compared to the fasting state. If humans experienced a similar jump, our bodies would literally overheat. As digestion progresses, the python's skin stretches around the still visible outline of the impala. Each movement of its ribs helps push gases out and maintain stability. There's no chewing, no division into pieces. The enzymes do all the work. The bones dissolve first, followed by soft tissues. Even complex structures like hooves are slowly broken down over days. The remaining hair is compacted and expelled later in a small, dry mass. Researchers found that this metabolic surge can last for more than a week, depending on the size of the prey. During this time, the python remains hidden and inactive, protecting itself from predators while the body works in silence. The external calm masks an internal storm of chemical reactions. But perhaps the most fascinating discovery is how reversible this process is. After digestion, the organs shrink again and the metabolic rate drops to nearly zero. The snake re-enters a state of near hibernation, capable of surviving months without another meal. Some individuals have been recorded surviving half a year on a single antelope. In evolutionary terms, this is efficiency perfected, energy stored, processed, and preserved with minimal waste. If humans possessed even a fraction of this metabolic adaptability, famine and overnutrition would vanish. The python embodies a design that's both ancient and futuristic, a creature that eats rarely but completely, turning matter into motionless endurance. Inside its body, what seems monstrous becomes a lesson in sustainability. Every molecule of its prey becomes new muscle, new energy, new life. The impala disappears, but nothing is lost. Nature recycles everything, even death, into survival. The African rock python is more than a predator. It's an evolutionary prototype. Its biology has challenged scientists for decades, revealing adaptations so extreme they border on the impossible. A single meal can sustain it for months. After swallowing an impala, its metabolic system enters a state of hyperefficiency. Oxygen use increases by over 40 times, but once digestion ends, it returns to near zero. No mammal can match this flexibility. For humans, maintaining such control over metabolism would revolutionize medicine, from obesity treatment to long-term space travel. Even its digestive chemistry has inspired science. Researchers studying python enzymes discovered compounds capable of breaking down collagen and bone faster than any known mammalian process. These molecules are now being studied for biomedical use, especially in tissue regeneration and controlled protein breakdown. What the python does effortlessly, we are still learning to imitate in laboratories. Another astonishing trait lies in its sensory system. Those small pits along its lips, the heat sensors, function like organic infrared cameras. They detect temperature differences as small as 0.003 degrees Celsius. In total darkness, the python sees heat itself. To the impala, night offers safety. To the python, its full visibility. Its cardiovascular system is equally remarkable. During feeding, the heart expands and thickens to handle the surge in blood pressure, then returns to its normal size within days. It's a reversible hypertrophy, something that would kill a human but keeps the python alive. Scientists have used this phenomenon to study heart elasticity and repair mechanisms that could help prevent heart failure in people. And the scale of its hunting ability defies imagination. Verified reports in Africa show pythons measuring over 6 meters, swallowing prey up to 60 kilograms, nearly equal to the snake's own body weight. In one documented case, a python consumed a full-grown antelope. The process took more than 4 hours, but digestion completed it in less than 2 weeks. These capabilities make the python not only a symbol of power, but also a living encyclopedia of biological engineering. Every function, from digestion to sensory detection, reflects the most refined logic of evolution, efficiency through adaptation. In the wild, such precision isn't luxury, it's survival. A single failed ambush could mean months without food. Yet nature designed this predator to thrive on scarcity. It doesn't chase abundance, it optimizes what it already has. To watch a python is to witness evolution at its most elegant, a creature that turns stillness into strength, silence into success, and patience into power. In nature, survival isn't about violence, it's about precision. The African rock python doesn't kill out of hunger or cruelty. It acts according to a design older than memory. Every movement, every coil, every pause follows a rule written by evolution. Conserve energy, calculate, endure. When the impala's heartbeat fades, the savanna doesn't mourn. It continues. Life transforms, energy flows, and the cycle resets. What disappears in one form reappears in another, in the python's muscle, in the soil that receives the remains, in the balance that keeps the ecosystem alive. This is the logic of nature. Nothing is wasted. Even death becomes resource. The predator and the prey are not opposites, they are collaborators in the continuity of life. The python teaches us that strength doesn't always move fast, sometimes it waits. Patience can be as deadly as speed, and silence can be as powerful as sound. For scientists, this creature remains a model of biological mastery, an organism capable of surviving extremes that would destroy most others. For the rest of us, it's a reminder that perfection doesn't need complexity. It only needs time. In a world that glorifies noise, the python thrives through quiet control. It doesn't chase opportunity, it creates inevitability. Its story is not one of death, but of balance, of energy transformed and precision rewarded. Because in the wild, beauty isn't in mercy or chaos. It's in the code, the design that keeps every species connected through adaptation and consequence. If you believe that nature hides its greatest genius in silence, subscribe and keep exploring with us. There's still much more to uncover, because evolution never stops teaching.